So hopefully once we finish the integration, we got it down to 1/2 times the limit as b approaches infinity of 1 plus x squared. So any questions on how I did the integration before I plug in my bounds? So now I'm ready to use my fundamental theorem of calculus. Again, leave the 1/2 in the front. I want to find the limit as b approaches infinity. Again, I'm going to plug in b for x, so I have the natural log of 1 plus b squared minus the natural log of 1 plus, and again, I know negative 1 squared is just going to be a 1. So the big question is, what's happening with the limit as b approaches infinity of the natural log of 1 plus b squared? Is that think about the natural log graph. What's happening with natural log? Is it approaching a fixed number? Do you have a horizontal asymptote? No. Log functions, remember, have the vertical asymptote, but there is no horizontal asymptote. So the behavior, remember, of your natural log is it's going towards infinity. It's not increasing quickly, but it is going to infinity. So can I find this limit? No. So this is an example then, again, doesn't matter that this is approaching a number, that's a value. You can't take something that doesn't exist and add a number to it. So this isn't a case where this is your integral that's going to diverge. So there is no solution here. We just simply say the integral is diverging. All right. So any questions on when you have an improper integral that is going to diverge? Okay? One part diverges, the whole thing diverges.
Can you explain how it diverges again?
Can
you explain how it diverges again?
What the word diverges mean? Or
No, why?
Because you can't find this limit. If the limit doesn't exist, we say it diverges. Because this limit does not exist right here. Converges. This one converged because we could find the limit. This one this one doesn't diverge because we can find this limit. The limit of 1 over e to the b squared was just 0. So we say that converges. Diverges is when you can't find the limit. Okay? So suppose that the lower bound, if the lower bound is negative infinity, we have to take the same approach. So if your lower bound is negative infinity, we're just going to use a different letter to distinguish between the upper bound and lower bound. Then we would say the limit as a approaches, instead of positive infinity, it's going to approach negative infinity. So again, the integral is going to converge if the limit exists, and it will diverge if it does not. So you still have to do the whole limit idea. So your improper integral of f. Now let's suppose that you end up with both upper bound and lower bound of infinity or negative infinity, because that could happen. If you have both an upper bound and lower bound that's infinity or negative infinity, you have to split the integral at some particular value. C just represents any number. The easiest place to split your integral, split it at 0. Because we know when you're dealing with a definite integral, the easiest one to evaluate is when you're at x equals 0. The only time you could not split it at 0 is if you had a vertical asymptote or infinite discontinuity at 0. Otherwise, you could split it at any number you want. But again, split it at 0, it makes it the easiest place. Just like the others, it's going to converge if the limit exists, and it will diverge if the limit does not exist. Now, when you are talking about divergence, if one of these integrals diverges, the whole thing diverges. So when you split it, you're splitting this into two different integrals. So if either one of these, all it takes is one to diverge, the whole thing will diverge. So let's take a look at example 2a. Again, pretty obvious you're dealing with an improper integral. What'd you say?
For the blank.
Yeah, it doesn't, I filled in my own. So just like what we've been saying, it converges if the limit exists. It diverges if the limit does not exist. Same thing. Okay?
If you just put 1, it works. Like it is blank. If you put the word 1.
Oh, okay. Thanks. Let's take a look at 2A. So you agree with me we're dealing with an improper integral? Yes. So again, it's the lower bound, so the first thing I'm going to do is rewrite this as the limit as a approaches negative infinity from a to 3. So now you want to do integration. What does this look like it's set up to be? Inverse tangent. So go ahead and finish that integration for me. So now I'm going to use my fundamental theorem of calculus, plug in my upper and lower bound. So I have the 1/3 times the limit as a approaches negative infinity. Again, I'm just leaving that 1/3 out. Again, I'm going to plug in my upper bound of 3. So again, 3 divided by 3 is 1. So I'm looking at the inverse tangent of 1 minus plug in your lower bound, the inverse tangent of a over 3. Well, what is your inverse tangent of 1? Inverse tangent of 1 is just what? Pi over 4. Now you need to remember what that inverse tangent graph looks like. Because again, I need to figure out what's happening as the inverse tangent is going to negative infinity. Well, let's think about tangent of x. Just your regular tangent of x graph. Tangent of x has vertical asymptotes where? Pi over 2 and negative pi over 2. So then I know inverse is what happens instead of having vertical asymptotes, you're going to have what? Horizontal. So remember your graph of the inverse tangent, and you will need to remember this. The graph of your inverse tangent is going to have a horizontal asymptote at pi over 2. It has a horizontal asymptote at negative pi over 2. And it looks a lot like your cube root graph. Because now it depends upon whether or not you're looking at the limit of inverse tangent going to positive infinity or negative infinity. As you're approaching negative infinity, what y value is the graph getting really close to? It's getting really close to negative pi over 2. So again, taking as you're getting really, really large divided by 3, no matter what, it's still getting really close to negative pi over 2. So we have pi over 4 minus negative pi over 2. So that's what happens with inverse tangent as you're approaching negative infinity. So again, your final answer will just be 1/3 times pi over 4 plus pi over 2. And you don't need to worry about, you can multiply it out and add them together if you want, but you don't have to. Yes, Tyler?
Isn't the constant in the front 3 from the degree of the
Well, first you pull out the 1/9, because you have to pull out the 1/9 to do the inverse tangent.
Oh.
And then you multiply by 3, so 3 times the 1/9 is the 1/3. So any questions on that one? So now let's take a look at B. So in this case, B, both your lower bound and upper bound are positive infinity. So what you have to do is you have to split your integral. The easiest place to split it is at 0. As long as you don't have a vertical asymptote at 0, you can always use 0. You can pick another number if you want. You could pick 1, you could pick -1, you could pick any number that you want, but the easiest one to use is 0. So when I split this, I'm going to calculate the area under the curve from negative infinity to 0 of x over the square root of 2 plus x squared dx. Then I'm going to add that to the area under the curve from 0 to infinity. So like I said, when you've got your bounds that have negative infinity and infinity, you've got to split it at some real number. You can split this at any number you want, but again, the easiest one to use is 0. How am I going to integrate? U sub. So go ahead and integrate. See if you can come up with what an integral is going to look like. and then we'll talk about the all raised to the 1/2 when we integrate. Again, after I do my U sub. So we all come up with the 2 plus x squared to the 1/2. Again, you have to divide a 1/2 out. Remember, this is going to be u to the negative 1/2. So when I add 1, that's going to give me a u to the 1/2 divided by 1/2, so I multiply by 2. So are we okay? We got 2 plus x squared all raised to the 1/2 power. Okay. So now that I know what each of that integration is going to look like, so what I am going to do, first of all, I have to do my limit notation. So I have to do the limit as a approaches negative infinity of my integral from a to 0 of x over the square root of 2 plus x squared dx. I'm adding that to the limit as b approaches infinity from 0 to b of x over the square root of 2 plus x squared dx. Now, all it takes, if one of these integrals diverges, the whole thing is going to diverge. So we already know what this integration is going to look like. So what I usually do when I have these two integrals, I do two different rows. So I'll have the limit as a approaches negative infinity. And again, I know what this integration is going to look like. It's just going to be that 2 plus x squared all raised to the 1/2, and I have to evaluate this from a to 0. I'm going to take whatever this is, I'm going to add it to the limit as b approaches infinity of 2 plus x squared to the 1/2. Again, I have to evaluate this from 0 to b. So using my fundamental theorem of calculus, I have to find the limit as a goes to negative infinity. Plug in my 0, so I have 2 plus 0 squared raised to the 1/2 minus 2 plus a squared raised to the 1/2. So now if I take a look at the second one, I have the limit as b approaches infinity of 2 plus b squared raised to the 1/2 minus 2 plus 0 squared raised to the 1/2. So the big question is what's happening with these limits. All I need is for one of them to diverge, the whole thing diverges. Think about what the square root function looks like. Is there a horizontal asymptote for your square root functions? No. So what's happening with these limits right here? They are doing what? Approaching infinity. So do these limits exist? No. So what do we say about this improper integral? Is it going to diverge or is it going to converge? Diverges. Again, this is approaching infinity. So this limit does not exist. So therefore we say that this improper integral is going to diverge. So like I said, some of these improper integrals, you can't solve them. You're not going to get an answer, so we just simply say it diverges. All right, so any questions on that? So any questions on what happens when they diverge? Last type of improper integral is when you have integrands that have infinite discontinuities. So what that means, your bounds aren't infinity or negative infinity. However, what's happening is one of your bounds is going to have a vertical asymptote. So again, what happens when you have a vertical asymptote? You have a definite integral going from a to b, but one of your bounds is going to be a vertical asymptote. So you still have to use the limit idea because I want to calculate the area under the curve as we're getting really, really close to b without being equal to b. So what we would do, if your upper bound is a vertical asymptote, we say the limit as k is approaching b from the left. Because again, if you look at this graph, if the upper bound is your vertical asymptote, you're calculating the area to the left of b. So what we'll do is we'll replace b with some arbitrary letter that I'll call k. And again, we're going to find the limit as you're approaching that upper bound from the left. All right? So you're not doing infinity anymore, you're doing the constant. Again, just like all the others, the improper integral will converge if the limit exists. And if the limit does not exist, then the improper integral will diverge. These are not as obvious improper integrals. So that, like I said, anytime you're now dealing with a definite integral, you've got to check, because they're not as obvious when you have bounds of infinity or negative infinity. Again, if your lower bound is your vertical asymptote, then you're going to find the limit as you're coming from the right. So, for example, from the graph, if your lower bound is your vertical asymptote, notice you're trying to find the area to the right. So that's why we would say the limit as k is approaching a from the right. Again, it converges if the limit exists, diverges if it does not, just like in all the other cases. It's also possible to have infinite discontinuity at some particular point C between your bounds. So what you're going to have to do is you have to split your integral at the point of discontinuity. If either one of these integrals diverges, then the whole thing will diverge. So all it takes is for one of these to diverge and the whole thing. They both have to converge in order for the limit to exist. So let's take a look at these. These are the not as obvious improper integrals. Where is 1 over the cube root of x undefined? 0. So then you have an improper integral because you are discontinuous at x equals 0. So what we're going to have to do is we have to write this as the limit as k is approaching 0 from the right. Because again, if my lower bound is my vertical asymptote, I'm looking at the area to the right of the lower bound. So I'm looking at the limit as k approaches 0 from the right, from k to 8. I'm going to write this as x to the negative 1/3. Guys, go ahead and integrate x to the negative 1/3 for me. So again, use my fundamental theorem of calculus. I'm going to leave my 3/2 factored out. I'm going to find the limit as k approaches 0 from the right of 8 raised to the 2/3 minus k raised to the 2/3. So 3/2 times. What is 8 to the 2/3? 8 to the 2/3 is 4. Now, to find the limit as k approaches 0 from the right, all we're going to do is do a direct substitution. Plug 0 in for k, so I'll have minus 0 to the 2/3. So 3/2 times 4 is just equal to 6. So is this going to converge or is this going to diverge? Converge. What that means is the area under the curve, it's converging. It's getting really, really close to a value of 6, but not equal to 6. That's what converging means. You're getting really close to it without being equal to it. All right, so any questions on that? Take a look at B. Is this improper? Why? There's discontinuity at your upper bound. Exactly. So there's discontinuity at x equals 4. Like I said, you guys now have to be on the lookout for improper integrals for any definite integral. These are not as obvious as when you have a negative infinity or infinity as one of your bounds. You guys now have to be on the lookout for this every day forward. So again, I'm going to have to rewrite this as the limit as k approaches 4. Now, when your upper bound is your vertical asymptote, you're not looking to the right, but you're going to be looking to the left. And again, it's going to be from 0 to k of 1 over the square root of 4 minus x dx. Do you have to do a u sub on this? Yes. Go ahead and integrate that for me. So when we integrated, we end up with negative 2 times 4 minus x to the 1/2. So any questions on how I integrated before I talk about the fundamental theorem of calculus here? So now I'm ready to go ahead and plug in my upper bound and my lower bound. So again, I can pull the negative 2 out. I want to find the limit as k approaches 4 from the left. Plug in my upper bound of 4 minus k to the 1/2. Minus plug in my lower bound, 4 minus 0 to the 1/2. Again, I'm just leaving that negative 2 on the outside. How do I find this limit as k approaches 4 from the left? I'm simply going to do what? I'm going to do direct substitution. So what's that limit going to be? It's going to go to 0. Minus 4 to the 1/2 is just what? 2. So then negative 2 times negative 2 is going to give me a 4. Does this converge or does this diverge? Converges. So any questions, guys, on how you handle the improper integral when one of your bounds is discontinuous or the vertical asymptote? Are we good? All right. Last one. Why is letter C an improper integral? It's discontinuous where? It's going to be discontinuous at x equals 2. So like I said, sometimes the discontinuity occurs not at your bounds, but it occurs between your bounds. So what you have to do is you have to split the integral at the point of discontinuity. So we have to split this up from finding the area under the curve from 1 to 2 of 1 over x minus 2 to the 2/3. Add it to the area under the curve from 2 to 4 of 1 over x minus 2 to the 2/3. So again, I know that I've got my discontinuity occurring at x equals 2. So when my upper bound is my point of discontinuity, remember I'm going to take the limit as x approaches 2 from which side, the right or left? Which side am I going? Again, think about it. If you're going from 1 to 2, I'm finding the area from 1 to 2. Am I to the right of 2 or left of 2? Left. So I'm finding the limit as x approaches 2 from the left. From 1 to k, and I'm just going to write this as x minus 2 to the negative 2/3. I'm sorry? Oh yeah, k. I'm sorry, I wrote an x. You're right, k. Thank you. Plus. So now my lower bound is the point of discontinuity, so I want to find the limit as k approaches 2 from the right, from k to 4 of x minus 2 to the negative 2/3 dx. All right. So any questions, guys, on how I split the integral when I've got the point of discontinuity between my bounds? Go ahead and integrate x minus 2 to the negative 2/3 for me, and then we'll deal with the limit. Times x minus 2 all raised to the 1/3. Okay? So what I usually do is I split this up into 2 rows. So what I'll do is I'll take this first integral, and I'm going to figure out what this limit's going to be. And then I take my second row, I figure out what that second integral is going to be. And then if those values exist, I would add them together. So again, I'm going to pull out the 3, and I'm going to find the limit as k approaches 2 from the left. So again, using my fundamental theorem of calculus, I've got k minus 2 to the 1/3 minus 1 minus 2 to the 1/3. So I have the 3 in the front. What is the limit as k approaches 2 from the left when I do my direct substitution? That's simply going to go to what? 0. Minus. 1 minus 2 is a negative 1, and what is the cube root of negative 1? Negative 1. So 3 times 1 is just going to be 3. So any questions where I got the 3 from? So now I'm going to plug in my upper bound and lower bound into my second integral. So again, I'm going to pull the 3 out, find the limit as k approaches 2 from the right, plug in my upper bound of 4, so I have 4 minus 2 to the 1/3, minus plug in my lower bound, k minus 2 to the 1/3. So I have 3 times. Well, 4 minus 2 is just a 2. 2 to the 1/3 is the same as the cube root of 2. Minus, when I do a direct substitution, plugging in a 2, 2 minus 2 is going to give me a 0. So I end up with 3 times the cube root of 2. Is this improper integral going to end up diverging or converging? Converging, because both these limits exist. So now I just need to add those two values together. So it's converging to 3 plus 3 times the cube root of 2. And again, like I said, it converges. Okay. Worst case scenario is I could give you one where you have infinity and or negative infinity in a bound, and then you have a point of discontinuity between your bounds. Or you could have one of your bounds being a point of discontinuity, the other bound being infinity, and having another point of discontinuity in the middle. Those are ugly. But they could happen. They could happen. All right, but they're all improper. Any questions on, you've survived another chapter? All right, so like I said, guys, the